Hi guys. So now I hope you had a chance to work it out. So let's solve this together. So what is potential energy? So we said that potential energy, right? This is equal to the work done by external force, right? To take the object from the reference point to the given point. So work done by external force from A to B, and this is also equal to negative of the work done by the electrostatic force, right? Negative work done by electrostatic force again when the object goes from A to B, right? Okay, so now we have to find the work done by the force of, let's say this plus Q2, there will be a force of repulsion, right? So when the object moves from here, this charge is pushing it away, right? It's pushing it, and while it's being pushed, this charge is moving from here to here, so it's doing some work. That work is your W electrical, so let's WE, so let's find it out. So WE, right, would be equal to what? This would be equal to integral F dot ds. Right? Now here, for simplicity, I have taken the movement is, the charge is moving in a straight line, right? So F and ds, so what is the direction here? So direction of F is going to be in this direction, and ds also is in the same direction, right? Because the displacement same direction. So if I take any small displacement, if I take this displacement here, my ds is going to have this direction, and the force also has the same direction. That's what I'm trying to say. So now, so the angle between them is going to be 0, right, between F and ds. So I can write this as, this is equal to integral F ds, right? And here what is my, so now what is my F and ds? Now let's start working on this carefully, right? Now what I'm going to do is, so first thing, is the force constant? No, it's not constant, right? Force is changing. So I can't just take F out of the integral, right? Now what is the force? Now let's go back to Coulomb's law, right? So when this object is moving at any point, let's say, let me take some arbitrary point here, right? This point, now this distance is r, this distance, right? This distance is r, and I will take a small change in r, right? Let's say this is the small change, and I'm going to call this dr, okay? R is the distance, and this is my dr, okay? So now let's find the work done by the electrostatic force when the object undergoes this displacement. So what is that going to be? So my work done during this, for work done by this force for this displacement, I'll call it dWe, right? dW electrostatic, right? This is going to be F into ds here is my dr, right? F dr, and this is, and what is F? F is going to be K. K is nothing but 1 upon 4 pi epsilon naught. I'm just calling it K here. So K, and this would be Q1 and Q1 into Q2 upon R square into dr. Right? This is going to be the work done during this elementary small displacement, and the total work done, right? This would be nothing but integral dWe, right? And this would be integral K Q1 Q2 upon R square into dr, right? And when we do integration, we have to talk about now the limits on this variable, right? So what is the value of R? So R would go from this value to the final value, right? So now let us say I'm calling this initial value, this I'm calling RA, this distance I'm going to call RA, right? And by the same token, from here to here, this total distance I'll call RB. RB would be, let me use a different color. This is going to be my RB, okay, up to this point. Okay? So this is my RA, this is my RB. So this is, the limits are going to be from RA to RB. Okay, so now it's fairly straightforward. Now just mathematics, physics is over. So we'll say WE equals, take the K, Q1, Q2 outside the integral because they're constant, K, Q1, Q2, and we have integral of 1 upon R square, which is nothing but, so x to the power n integral would be x to the power n plus 1 upon n plus 1, so this would be nothing but R to the power minus 2 plus 1 divided by minus 2 plus 1, right? I'm just doing it step by step, right? This is the exponent, and the limits would be from RA to RB, and this is minus 1, right? So this would be K, Q1, Q2, right? And this is nothing but 1 upon R, right? and this would be, so this minus I'll bring it out, so this would be into Q1 Q2 into minus, right, this into minus, and what do we have here? So we have 1 upon R, so this is 1 upon RB minus 1 upon RA, right? And since there is a minus sign here, so I can take it inside and change the sign, so this would be K Q1 Q2, right, into 1 upon RA minus 1 upon RB. Okay. Now here I took the reference point A, right, and then I calculated the potential energy. Now typically in most cases, right, it's convenient and conventional to say that we will calculate the potential energy with respect to the starting point being infinity. Once again, we'll very commonly, right, in most cases we'll calculate the potential energy when the reference point is at infinity. Okay, so the point A is not here, the point A is now at infinity. So now when we find, now if A is infinity, then what does RA become? This point was not here. Now what you're saying is, instead of bringing it from here to here, let us say infinity is somewhere, well, obviously infinity is indefinitely, away. So you bring it from infinity, right, then the work done would be the same thing, but my RA is going to be infinity. So now I'll say WE, right, when infinity is my reference point, this is going to be K Q1 Q2, right, into 1 upon infinity minus 1 upon RB, and this 1 upon infinity is nothing but 0. So now I get here that my work done electrostatic, right, for infinity as a reference point, this is going to be nothing but K Q1 Q2 upon RB, right, with a minus sign, and there's a minus sign here, right, minus. And what is my potential energy? Potential energy is nothing but, P is nothing but negative of the work done, right. So P is negative of work done, so I'll say my potential energy is equal to minus of minus K Q1 Q2 upon RB. So my P is equal to K Q1 Q2 upon RB. So this is the potential energy of the system when I take infinity as the reference point. And in general, if the two objects are separated by distance r, here now remember this RB is the final point, RA is from where it starts. So basically we're talking about the potential energy of the system when the distance between them, straight line distance between them is RB, right. So now we'll say that PE, so instead of RB I'll just call it R now, right. So when Q1, Q2, right, Q1 and Q2, the distance is R, then we'll say potential energy of such a system is nothing but K Q1 Q2 upon R. Very nice and very, very simple, right. So two charges separated by distance R, and when we take infinity as a reference point, then this is their potential energy, right. Now we'll build on this as we move forward, but this is something that I want you to understand. So please go through this very, very carefully, step by step, and make sure you can do this derivation on your own.